Okay, so here's another stoichiometry lesson. It's going to be very similar to a lot of the other ones we've done here. Gas stoichiometry. You're going to have to use the ideal gas law a few times through this. You'll also have to have a pretty good understanding of STP and SATP. Don't you worry, I'll make sure I remind you about that as this lesson goes on. Let's get rolling. So we're going to cover gas stoichiometry today. This is where we'll know details such as concentration, about gases being mixed, blah, blah, blah. That's just a mess of a sentence. Basically, we'll just know a bunch of stuff. We'll know like the temperature, pressure, all that, whatever, right? Just like the other day, this is not in our Unit D booklet. This is in that new handout. That's the one that said gas stoichiometry on it. It's really short. There's just two questions, two example questions we'll run through, just like that solution stoic lesson from a couple days ago. And it's also going to be a pretty quick lesson today. Anyway, I'm not going to waste your time. Let's run. So here we go. First question. An 8.2 sample of 8.2 gram sample, I should say, of pentane, which is C5H12, is burned. How many liters carbon dioxide would be produced by the reaction if the temperature was 34.0 degrees Celsius and the pressure was 111 kilopascals? One thing that stands out before even step one, before I even read that sentence, is we see degrees Celsius, which unfortunately, as much as it's nice for day-to-day temperature, degrees Celsius is not that useful in chemistry. We have to turn this into Kelvin. To go from Celsius to Kelvin, remember, we have to add that magic number, 273.15. So this 34.0 degrees Celsius right off the bat is actually 307.15 Kelvin. So keep that in mind. You want to write that in before you do anything else. Anyway, step one, write a balanced equation. Imagine that. Like, can you imagine we're actually making a balance equation through all this? It's almost like we've been doing this a million times. But let's do this. Let's stop whining. If we're burning pentane, that's a hydrocarbon. So this is going to be hydrocarbon combustion. We'll have C5H12 plus oxygen. And that's going to produce two things. It's going to produce CO2 and it's going to produce H2O. That's just classic hydrocarbon combustion. That's always gets produced when you're burning a hydrocarbon. Now it does say a balanced equation, so let's look at what we got here. I see we have five carbons, but only one carbon here, so maybe I'll put a 5 here. If we have to erase it, we have to erase it, no big deal. The other thing I'll look at is we have 12 hydrogens here, but only 2 hydrogens here, so I got to put a 6 here to make that 12. And then I guess since carbon and hydrogen are now balanced, let's look at our oxygen count. 5 times 2 is 10 plus 6. We got 16 oxygens on the right-hand side. On the left-hand side, though, we only have 2. So to turn 2 into 16, I guess we just have to put an 8 in front of that. So that's now balanced. We're all good to go on that. We'll have to come back to that later. But neat. There we go. Cool. Step 2, calculate the number of moles of given. Well, here's the thing. We know a given temperature and we know a given pressure, but that's not a quantity. That's just a kind of a characteristic of the environment you're in. The only quantity we're given is the fact that we have 8.2 grams of pentane. Now, if we're looking for the number of moles of what was given, that is, I guess, what we have to say is given. To turn grams into moles, you need your molar mass. So let's start by finding the molar mass of pentane. That's 5 carbons, so 5 times 12.01, plus 12 hydrogens, so 12 times 1.01. And that's going to equal 72.17 grams per mole. So I guess what we need to do next is just take that number, 72.17, and set that equal to some number of grams, which we have, 8.2, over some number of moles, which I'll just call n. To solve for n, times by n and divide by 72.17, and you're going to see that n is going to equal, and I'm going to keep as many digits as I possibly can, 0.113620,618 moles. And just to make sure we're all on the same page on this one, I'm going to say that this is our number of moles of C5H12. That's a pentane. Okay, it's important. Next step here, moving on to step 3. Use your molar ratio, those are your coefficients in your balanced chemical formula, to calculate the moles of the required chemical. Let's look back at our actual question itself. It's asking how many liters of carbon dioxide, so that's going to be our required chemical, would we produce, blah, blah, blah. So since carbon dioxide is our required, let's go back to our balanced chemical equation. We only have one part of our pentane, but we have 5 parts of CO2. So what that basically means is this number we found for a number of moles of C5H12 of pentane, that only represents one part. Okay? In a balanced chemical equation, these numbers out in front, these coefficients in front of all of our different compounds, represent the molar amounts in terms of a ratio. So one part of this means we have 5 parts of this. Think of it like a recipe. I don't know why I've never made that analogy before. They often say, oh, like, oh, I add 1 part of celery and 5 parts of, broccoli or whatever. I'm just throwing things in here. That's all we're doing, right? So molar ratio, it has to be a part to a part. So since we have 1 part of C5H12, that's this amount right here, we just need to times that by 5 to figure out how many moles of carbon dioxide we have. So again, just times that old number by 5. I'm not going to rewrite it out. It's on your page already. But the new amount for our number of moles of carbon dioxide is 0.5681030.899 moles. Feels like I'm like saying a phone number or something. Keep as many of those sig digs, or as many of those digits, I should say, as possible, because of course, every little bit counts. We don't want to be off in our final calculation. You round to sig digs only in your final calculation. So anyway, that's it. All right, step 4, use the moles to calculate the required variable. So look at what we're actually requiring here. We're looking at number of liters, rather. We're looking at the number of liters. We have a temperature. Again, we'll need to use that in Kelvin. So it was 307.15. It should already be on your page, but there you are. So we want liters, I should say. We have a temperature. We have a pressure. And we also have a number of moles. That was just what we had on the last slide there. It's almost like there should be a chemical, or rather a formula that actually like combines all these different variables together, right? It's almost like it'd be really ideal if we had that. Anyway, this is why I'm teaching from home now. PV equals nRT. So PV equals nRT, that's going to be our formula. It's the ideal gas law. Just remember R, by the way. That's the odd one out there. R is always 8.31. It's just a constant. You know, it is what it is. That's a terrible R. Let's try that again. There we go. That's a little bit better. So R is always 8.31. Let's just throw the stuff in here. Let's get this done. You guys are already like, you know what? Just get over it, Scott. Anyway, 111 times V equals N. I'm going to copy that down again, just to be really exact here. 0.5681030.899. That's your N, that's your number of moles, times by R, which is 8.31, times by T, has to be in Kelvin. Temperature has to be in Kelvin, not in Celsius. So 307.15. Just looking at this, I can tell I'm going to multiply this whole mash together and then divide away this 111 to get V all by itself. So V all by itself, and you know what, we'll even say round to sig digs. 2 sig digs is how many sig digs we need here. So V is going to equal 13 liters. That's it, right? So in other words, if you had 8.2 grams of pentane and you burned it, and every last drop of that pentane burned, you would have 13 liters of carbon dioxide being produced by that. That's a lot of carbon dioxide. There you go. All right, cool. Example 2, next page. Whoop. All right, how many grams of aluminum would be need? Is that really what it says? Yeah, it even says that in your booklet, would be need. How many grams of aluminum would be need to completely consume 4.54 liters of chlorine at STP? Let's hold up here for a second. STP. I know this one's always a tough one to figure out. Here's what I always think of it. As far as we're concerned, STP was the original standard temperature and pressure. And this is the one that I thought was always kind of silly. I thought they kind of like goofed up when they made it, because their standard temperature was 0 degrees Celsius, which why on earth would a room be 0 degrees Celsius? I have no idea. But again, also we turn that into Kelvin, so 273.15 Kelvin. As for the pressure, this is what I always have a hard time remembering this, but I always think just to go like part and parcel with how weird STP is, the standard temperature and pressure is 101.325 kilopascals. So again, also a weird amount. That's at least how I always remembered it. Okay. Anyway, step 1. Now that we have that out of the way, step 1, write a balanced equation. We're mixing aluminum with chlorine. As weird of a reaction as that sounds, that is what it is, right? So aluminum is just Al, it's just aluminum metal, plus chlorine. Chlorine does not exist on its own unless it's an ion. It's not an ion in this case, it's probably chlorine gas, so it's got to be Cl2. Aluminum plus chlorine gas is going to combine to produce, of course, a compound. This is just a single element plus a molecular version of an element. So this is a formation reaction, so it's going to become aluminum chloride. Aluminum chloride, of course, would be an ionic compound, so you got to watch the charges. Aluminum has a +3 charge. Chlorine has a -1 charge. So swap and drop that. We'll need 1 aluminum, and we'll need 3 chlorines. So AlCl3. Okay, so again, that was just ionic charges, and we're balancing the charges on that. That's all I did there, right? Next up, it's going to be a balanced equation. We have 3 chlorines here, but 2 chlorines here. I'm going to have to put a 3 in front of this to make 6 chlorines and a 2 in front of this. So now we have 6 chlorines. But now, oh, we got 2 aluminums here. So I'm going to have to put a 2 in front of here now. That's about all there is to that. Anyway, moving on. Step 2, calculate the number of moles of given. The only thing it gave us here was our volume of chlorine. Well, the good news is that's actually pretty much all we need. Remember, PV equals nRT. We have a volume, right? 4.54 liters. We have a pressure. Our pressure is 101.325 kilopascals. And we have a temperature right over here, T. We have temperature, that's 273.15 Kelvin. And then R is always 8.31. So we've got this, we got R, and we got T. So that's enough to find N. Let's throw these numbers in. Pressure is 101.325. Volume is 4.54 equals N, which is what we're looking for. R, which is always 8.31. T, which is, what was it again? Oh, 273.15. Hopefully you see it again N all by itself. I would multiply these two things together, and then I would divide away the 8.31, and then I'd divide away the 273.15. Long story short, our N on this case, another really bad phone number type number, is 0.20266100258 moles. And just so we take inventory of stock of this, this represents the number of moles of chlorine. So that's our Cl2. That's our chlorine gas. Okay, step 3. Use your molar ratio to calculate the moles of the required chemical. Well, we're looking for grams of aluminum. So before we get grams, we have to actually figure out, the number of moles of aluminum we have. So if we know how many moles of chlorine we have, let's look back at our balance formula. Notice that would represent 3 amounts. We have 2 amounts of aluminum. So this here is 3 parts, but we actually want to find how many moles 2 parts are. Well, I think the best way to do that would be to take this and divide it by 3. That would tell you 1 part. And then before you even write down that number, because who cares, let's just times it by 2. So if you divide this by 3, you get 1 part. Times it by 2, then you have 2 parts. Okay? I'll spare you the trouble of that. If you divide that number from the previous page by 3 and then times it by 2, you're going to get 0.135.107.3506 moles. And that is our number of moles of aluminum. Okay, that's 2 parts. Cool. Step 4, use the moles to calculate the required variable. We're looking for grams. We have moles. What connects grams to moles? Hopefully you know by now it's your molar mass, right? So your molar mass of aluminum, this is actually a really nice molar mass to deal with. For once in our life, we actually don't have to add a bunch of elements, molar masses together. It literally is just aluminum. So you look at your periodic table. The periodic table says that it's 26.98 grams per mole. That is the molar mass of aluminum. It's not like Al2 or anything. There's nothing else going on. It's good. We're good. We're done. Good. All right. So 26.98 grams per mole equals some number of grams. That's what we're looking for. Let's call it X over some number of moles. That was that awful number I just wrote on the last slide. It's 0.135.107.3506 moles. Whew. All right, so multiply that over to the other side. Long story short, you're going to have X equals to 3 sig digs, 3.65 grams, which is always hard for me to believe. That's not very much aluminum. That is just a small little clump of aluminum. That would be enough to completely consume 4.54 liters of chlorine. That's like bigger than a milk jug of chlorine. Wow, crazy. And that's at standard temperature and pressure. Wow, mind-blowing. Mind-blowing, I say. Wow. All right, so for practice, told you it was a quick lesson. We're only like 15 minutes in. For practice, I want you to do those worksheet questions in the handout. Also, go back and complete any unfinished questions from the previous sections in our Unit D booklet, especially yesterday's stuff on titrations, because I know that was such a long lesson. Make sure you go back and finish those questions. You got lots of extra time today. One last thing, if you haven't already handed it in, the acid-base titration steps task is due today. It shouldn't take long. I don't think it would take anyone more than about 10 minutes to get it through. Of course, if you haven't already watched that video from Thompson River University on how to do a titration, you've got to watch that first. Otherwise, you're not going to know how to do this. Anyway, I'm going to stop talking. Best of luck, guys. You know where to reach me if you need me, and good luck.